Now, so far we have been assuming that a smaller body, like an orange, is orbiting a much larger one, like the Earth. But in fact, actually, the Earth is also sort of orbiting the orange, or more specifically, both the orange and the Earth are orbiting their common center of mass. Because the Earth is so much more massive than this orange, the common center of mass is pretty much the Earth's core, but it's not exactly. And for most orbits, obviously, around the sun, the center of mass will be very close to the sun, and we won't really notice any difference. But it is important to note that in systems, for example, like the Earth's moon that we can see right here, the center of mass is actually not directly in the center of the Earth. So the Earth will also kind of wobble as each object orbits the common center of mass. This can become more extreme when we move to the dwarf planet Pluto and one of the satellites, and the center of mass is even further away. It's definitely outside any of the bodies. And even more extreme cases are seen here, where you're looking at binary stars. For binary stars, typically the center of mass, if they're sort of equal mass, will be way further away from each of them, and they will both have elliptical orbits around the prime focus, which is the center of mass. Now, how do you get the center of mass? You can essentially define the distance from both objects as the distance from one object 1 to the center of mass, and then the distance from the center of mass to object 2, which will be r2. And if you define those, then you can actually write the statement that the product of r1 times m1 will be equal to r2 times m2. And this is what you're going to be essentially using to actually solve problems not only of things orbiting the sun or satellites, but even when we move to exosolar planets. And sometimes what happens is one of these masses is going to be so big that essentially one of the distances becomes r, and you can kind of eliminate either r1 or r2. And with this definition, you can actually write Kepler's third law in a much more general way. If we keep r, but understanding that r is actually the sum of r1 plus r2, and actually understanding that here what we actually want for Kepler's third law in a general way is not to use just the mass of the sun, but it's actually the sum of the masses that are interacting. You can very easily get just the mass of the sun if you consider something like the Earth and the sun, because the sum is pretty much just the mass of the sun. But for systems where m1 will be relatively close to m2, you will need to use Kepler's law in this form. So what you also have in your lecture notes is a very quick example of how we would implement this for a binary star system. In this case, we're going to keep the eccentricity with the value e, so we don't know. In many cases, that may not be known to begin with. But this system has two stars, one with 4 solar masses, another one with 6 solar masses. And we know that the period is 50 years. So I will not go through the steps in super detail, but it's important just to highlight the kind of things you should be doing. So the first thing you should be doing is to write a statement that r1 times the mass of 1 equals r2 times the mass of 2. You've been using this for a lot of modules so far. This will allow you to simplify the problem. And in this case, I've chosen to write r as a function of just r2, but there's nothing special with it. You also need to calculate the total mass of the system, which will be just the sum of m1 and m2. This will be 10 solar masses, which in kilograms will give you this. And we then need to apply this general form of Kepler's third law. Remember that if you're going to use SI units, you need to convert the periods into seconds and use the gravitational constant in these units. If you do that, you can calculate that R2 is 1.75 times 10 to the 12 meters. You can then go back to the expression that relates R1 and R2 to calculate R1. And finally, you can find the total separation between both sources. The important thing is that this will be the average separation, and the furthest separation will actually be affected by the eccentricity. If we know the eccentricity, we could actually calculate this explicitly. If not, we would leave it like this. And if you do have questions about problems like these, just get in touch.